What if, at this very moment, inside a handful of secure research institutions across Europe, a small group of scientists is quietly studying a dataset that almost nobody else on Earth has seen? Not rumors, not speculation. Real measurements gathered by one of the most advanced deep space probes ever built. Data collected months ago and kept under strict silence ever since. For 4 full months, those readings have existed behind closed doors, analyzed carefully while the rest of the world moved on, unaware that something unusual may already be waiting inside those files. Stay with me, because the chain of events behind this story is far more intriguing than most people realize. If the mystery of 3I Atlas fascinates you, and you want to keep exploring strange cosmic events like this one, take a moment to hit the like button and show that you're part of this search for the unknown. Every bit of support helps keep investigations like this alive, especially when the story may be reaching its most important moment. Because the truth is, despite what the headlines suggested weeks ago, this story is far from finished. Many people assume the object known as 3I Atlas has already been explained. It appeared, scientists observed it, and then it continued on its path out of the solar system. Case closed. That is the impression many casual readers were left with. But science does not work that way, and silence in science rarely means the mystery has been solved. Often it means something is still being carefully examined. The quiet surrounding the events of November last year is one of the most unusual aspects of this entire situation. And to understand why it matters, we need to look step by step at what actually happened. Because by the end of this explanation, you will understand why a closed meeting scheduled for late March between multiple scientific instrument teams may be one of the most significant scientific discussions happening anywhere in the world right now, even though almost nobody outside the research community is talking about it. Let's begin with a simple question. When the most powerful deep space probe ever sent by the European Space Agency suddenly redirects its instruments away from its main mission target and instead focuses on a passing comet, what does that decision tell you? Pause for a moment and consider the scale of that choice. Not one instrument, not two operating as a backup observation. 5 different scientific instruments, each designed for highly specialized measurements, were all turned toward the same object at the same time. That level of coordination is not casual curiosity. It represents a deliberate decision that the object being observed deserves the full capability of the spacecraft. The spacecraft in question is called the Jupiter Icy Moons Explorer, often shortened to JUICE. Built and launched by the European Space Agency, this billion-euro mission left Earth in April 2023 with a clear purpose: to travel across the solar system and study the frozen moons orbiting Jupiter. Everything about the mission was designed for that goal. Its cameras, spectrometers, and particle detectors were all carefully engineered to examine icy surfaces and hidden oceans on those distant worlds. But in early November of 2025, something unusual happened. At that time, JUICE was positioned on the far side of the Sun relative to Earth. Communication signals had to travel around the Sun, which slowed the transfer of information dramatically. Data transmission during this period was already expected to be slow and limited. It was a moment when very little attention from the public was focused on the spacecraft, and that is exactly when the observation took place. On November 6, 2025, only a week after 3I Atlas passed closest to the Sun, the spacecraft's onboard camera system captured 12 separate images of the object during a single observation window. 12 images may not sound extraordinary at first, but the real significance lies in what else was happening simultaneously. While the camera was active, 4 additional instruments were operating at the same time. Spectrometers, particle detectors, and atmospheric analyzers all pointed toward the same comet-like body. Together they formed a coordinated observation package capable of measuring chemical composition, radiation interactions, and environmental effects around the object. This was not a quick photograph taken out of curiosity. It was a full scientific observation session using some of the most advanced instruments humanity has ever sent into deep space. And then something even more interesting happened. Because the spacecraft was positioned on the far side of the Sun, the data from that observation could not be transmitted quickly back to Earth. Scientists had to wait as the information slowly traveled through space, piece by piece, across millions of kilometers. Weeks passed, then months. Finally, in the last week of February 2026, nearly 4 months after the images were captured, the entire dataset arrived at the research centers responsible for analyzing the instruments. Now ask yourself an important question. When scientists receive a new dataset from space that might reveal something unexpected, what usually happens next? Normally, the scientific world becomes noisy. Researchers begin discussing the findings immediately. Preliminary analyses appear online, papers are drafted quickly, and debates begin across conferences and academic forums. But that is not what happened here. Instead, the team scheduled a closed meeting for late March, where the instrument groups will present their findings to each other before any public release. 4 months of waiting for the data, followed by another month of quiet analysis behind closed doors. And that silence is where the story becomes even more interesting, because once you compare this situation to previous interstellar visitors like Oumuamua and 2I, Borisov, a very different pattern begins to appear. The scientific response this time has been unusually careful, unusually coordinated, and far quieter than anyone would normally expect, which raises a question we cannot ignore. What exactly did those instruments see when they were pointed at 3I Atlas? And more importantly, why has the answer been kept silent for so long? Because before we even reach the measurements themselves, there is another set of strange observations connected to this object that appeared briefly in scientific reports, and then faded from public discussion almost as quickly as they arrived. Those early observations added another layer of mystery to the story, and they began appearing even before the deep space probe captured its images. Several observatories noticed something about 3I Atlas that did not behave quite like an ordinary comet. Normally, when a comet approaches the Sun, the increase in temperature causes frozen gases inside the nucleus to vaporize. That process creates the familiar glowing cloud of gas and dust called the coma, along with the long tail stretching away from the Sun. As the comet moves away again, the energy driving those reactions gradually fades. The comet cools down, the gas production slows, and the brightness steadily decreases. That predictable pattern has been observed countless times throughout the history of astronomy. Comets brighten on the way in and fade on the way out. But 3I Atlas did something that briefly puzzled researchers. Instead of dimming as it traveled away from the Sun, instruments aboard the SPHEREx observatory recorded a sudden flare in brightness. The object appeared to intensify, while already moving outward into colder regions of space. At first glance, that behavior might sound minor, but it runs directly against the standard models scientists use to describe cometary activity. When a comet is losing solar energy, its activity should decline. That is the expectation supported by decades of observation. In this case, however, the opposite occurred. Researchers quickly proposed a possible explanation. They suggested that the comet's nucleus might contain patches of extremely volatile material buried beneath its surface. As the outer crust eroded during its close pass around the Sun, these deeper pockets of volatile substances could have become exposed. Once exposed, they might release gas rapidly for a short time, producing the unexpected flare, even while the object was leaving the inner solar system. It is a reasonable hypothesis, and one that fits within known physics. Yet it also requires a very specific internal structure inside the comet's nucleus. The volatile materials would need to be arranged in just the right locations, so that they were uncovered at precisely the right moment to create the flare during the outward journey. That explanation remains possible, but it is not the only unusual observation connected to this object. Before the SPHEREx flare was widely discussed, several early reports mentioned something even stranger. Multiple telescopes detected signals that looked similar to cryovolcanism. To understand why that matters, it helps to know what cryovolcanism actually is. Unlike traditional volcanoes on Earth that erupt molten rock, cryovolcanoes release extremely cold substances, such as water vapor, ammonia, or methane. These eruptions occur on icy worlds, where internal heat pushes volatile materials upward through cracks in the surface. Examples exist in our solar system. The Moon, Enceladus, orbiting Saturn, produces dramatic jets of water vapor from fractures near its south pole. The distant moon Triton, orbiting Neptune, also shows plume activity. In both of those cases, the eruptions are driven by internal energy sources, such as gravitational tidal forces. Those moons are not inert objects drifting through space. They are geologically active worlds with complex internal structures. That is why the early cryovolcanic type signatures associated with 3I Atlas raised eyebrows among researchers. An interstellar comet traveling through our solar system for the first time should not possess the kind of sustained internal energy needed to produce organized eruptive behavior. Normally, such an object simply warms up, releases gas from its surface, and then gradually quiets down. Structured plume activity would suggest something more complicated happening beneath the surface. For a brief period, those observations circulated through scientific discussions, but they were never fully confirmed nor officially rejected. Instead, the topic quietly disappeared from mainstream coverage as attention shifted toward other measurements. And then yet another anomaly appeared. Astronomers detected a large halo of X-ray emissions surrounding the comet. The glowing region extended outward, roughly 250,000 kilometers from the nucleus. To understand the scale of that distance, it is almost equal to the average separation between Earth and the Moon. Comets can produce X-rays through a known process called solar wind charge exchange. Highly charged particles flowing outward from the Sun collide with neutral atoms in the comet's coma, generating faint X-ray emissions. Scientists have observed that mechanism before. However, the size and strength of the halo surrounding 3I Atlas appeared large enough to prompt further investigation. It was not merely a faint background glow, it was a structure extending hundreds of thousands of kilometers into space. At this point, the picture becomes more complex. An interstellar object enters the solar system. It shows hints of unusual activity resembling cryovolcanic eruptions. It produces a massive X-ray halo stretching across an enormous region of space. It flares unexpectedly while leaving the sun's influence. And then, a €1 billion spacecraft traveling toward Jupiter redirects 5 advanced scientific instruments to observe it in detail. None of these details alone prove anything extraordinary. Each one could potentially be explained through natural processes, but when they appear together as part of a sequence, the pattern begins to feel less ordinary. That is why the observations made on November 6th are so important, because those 5 instruments aboard the JU spacecraft were designed to answer very specific scientific questions. One of them, a spectrometer built to analyze icy surfaces, can determine the chemical composition of distant objects with remarkable precision. Another instrument identifies individual molecular species within thin atmospheres or gas clouds. A third measures the surrounding charged particle environment to detect unusual electromagnetic interactions. When those tools operate together, they create a complete diagnostic picture of what an object is made of and how it interacts with space around it. In other words, if anything about 3I Atlas behaved in a way that did not match ordinary comet physics, those instruments would be capable of detecting it. And that brings us back to the quiet period that followed the observation, because the measurements from those instruments have now been in the hands of scientists for weeks. Yet the world outside the research institutions still does not know what they revealed. Imagine being one of the scientists responsible for those instruments. Years of work went into designing them, testing them, and sending them across millions of kilometers aboard a spacecraft whose original mission had nothing to do with this object. Then suddenly, in November, the opportunity appeared to study a visitor from another star system in extraordinary detail. The instruments were activated. The observation window opened, and within a short span of time they collected one of the most valuable datasets ever obtained from an interstellar object. After that, the waiting began. Because the spacecraft was positioned far beyond the Sun relative to Earth, transmitting the information back home took months. Bit by bit, the data traveled across space until finally, in late February 2026, the entire dataset reached the teams responsible for analyzing it. Since that moment, the scientists have been examining the measurements quietly. No early leaks, no excited comments posted online, no rapid publication of preliminary results. Instead, the researchers scheduled a coordinated meeting in late March where all instrument teams will present their analyses together. Only after that discussion will the results likely begin appearing in formal scientific papers. That kind of structured approach is not unusual when researchers are dealing with complex datasets that require careful interpretation. Instruments like spectrometers and particle detectors generate enormous volumes of information. Each measurement must be calibrated, verified, and compared with known models before any conclusions can be drawn. Still, the level of discipline surrounding this dataset stands out. When earlier interstellar objects such as Oumuamua were discovered, the scientific conversation became public almost immediately. Researchers around the world debated its unusual acceleration and shape within days. Competing theories appeared rapidly, and the entire process unfolded openly in front of the public. The same thing happened when 2I Borisov entered the solar system 2 years later. Observations were shared widely, and conclusions emerged within months. This time, the process has been noticeably quieter, and that silence has led some observers to wonder whether the data might contain something unexpected. It is important to be careful here. Extraordinary claims require extraordinary evidence, and nothing publicly available proves that 3I Atlas is anything other than an unusual natural object. Everything described so far comes from verified reports, observational records, and mission updates released by official agencies. What has not been released is the actual interpretation of the data collected by the spacecraft's instruments. Those measurements may simply confirm that the comet contains rare chemical compounds or an unusual mixture of ices. They may reveal previously unseen interactions between interstellar material and the solar wind. Discoveries like that would still be scientifically valuable, even if they remain entirely natural. But until the analysis becomes public, we cannot know for certain. What we do know is that the object itself has already continued its journey. 3I Atlas has now passed beyond the orbit of Jupiter and is accelerating outward toward the dark region between the stars. Within a few years, it will be far beyond the reach of even our most powerful telescopes. Whatever secrets it carried with it when it entered our solar system are now traveling away again. The only remaining clues are the measurements left behind in the instruments that observed it during those brief months when it passed through our neighborhood. Somewhere inside those datasets could be the answer to a simple but profound question. Was 3I Atlas merely a strange fragment of material from another star system, unusual but ultimately natural? Or did it display characteristics that challenge our current understanding of how interstellar objects behave? If the answer turns out to be the first possibility, the scientific papers released in the coming months will describe it clearly. Researchers will update their models of cometary chemistry and interstellar debris, and the story will settle into the history books as another fascinating discovery. But if the data points towards something more complicated, the process of releasing that information will likely be careful and deliberate. Findings that challenge established assumptions often go through extended verification before being presented publicly. Multiple teams review the results. Independent analyses are performed. Every detail is checked and rechecked. That process protects the integrity of science, but it can also create periods of quiet while researchers work through the evidence. Right now we appear to be in one of those quiet periods. A group of scientists is preparing to meet in late March to discuss what 5 advanced instruments observed when they studied 3I Atlas from a distance of roughly 41 million miles. Once that meeting concludes, the first official reports will begin appearing in research journals and online preprint archives. When those documents finally arrive, they will present a clear, carefully written explanation of what the instruments detected. Yet even then, understanding the significance of those results will require attention from people willing to look beyond the headlines and examine the evidence closely. Because the universe rarely reveals its biggest discoveries with dramatic announcements. Instead, it offers clues through patterns, anomalies, and quiet datasets waiting to be interpreted. Somewhere within the readings collected during that November observation, may be one more piece of the puzzle about how our solar system interacts with the wider galaxy. Whether the answer turns out to be simple or surprising, the moment when those findings become public will mark the next chapter in the story of 3I Atlas. And if you want to stay ahead of that moment, following every update and uncovering the deeper mysteries hidden in space, make sure you subscribe to the channel, like the video, and join us in the next episode as we continue exploring the strange signals and unexplained phenomena that the universe keeps sending our way.